our latest results with you all. So I'm going to talk about extreme weather detection, and the outline of my talk is going to be the following. So we'll just start off slowly, so talk about the scientific motivation for why we care about extreme weather. Then I'm going to sort of take an important digression on computer vision and what's happening with deep learning in computer vision. We'll talk about some trends and successes there. Then we'll come back to climate science. So we'll talk about what we've been doing with deep learning in climate science. So our results that we have at this point in time and some open challenges. And then I'll do a little bit of speculation on the future of AI in climate science. Before I get started, I think I'd like to get a sense for the background of the crowd. So I'm told that there are a number of climate scientists and statisticians here, but how many of you are into machine learning? I guess if you could raise your hands. Cool, sounds great, thank you. And how about deep learning? If you're interested or have tried it so far, great. All right, that's great, thank you. All right, so scientific motivation. So I guess when we say in the talk, and I guess when we'll say extreme weather, what I mean are events like hurricanes, tropical cyclones, extratropical cyclones, atmospheric rivers. There are other many kinds of extreme events, weather fronts, mesoscale convective systems, so on and so forth. But this should be the exemplar picture in your mind when we talk about extreme weather. Now, the reason extreme weather, of course, is important is because of the impact on human society. So Hurricane Katrina, when it made landfall on New Orleans, clearly the local economy was devastated for maybe a decade. I think it's taken a long time for New Orleans to recover. But the impact on human life in terms of the displacement, apart from just the dollar amount of damage, is really quite significant. So it's something to keep in mind. Events like hurricanes hit important metropolitan centers as well. So this is the aftermath of Hurricane Sandy hitting New York City. So again, this accompanying storm surge resulted in a lot of damage in New York, and certainly brought the city to a standstill for a few weeks. So the question that we care about is how extreme weather, like tropical cyclones, like extratropical cyclones, is going to change in the future. When we say how will it change, specifically what we care about is how will the number of extreme events change, how will the intensity of extreme events change. So in order to address those questions, what sort of data can we possibly turn to? So what options do we really have? Well, one option is maybe to look back in time. So look at paleoclimate, get a sense for what extreme event statistics might have been in the past. But really, the only way to address this question of how things are going to change in the future is to look forward in time. So climate simulations come to the rescue. So I have a colleague, Michael Weiner, I guess in the room somewhere, who runs many different climate simulations. And certainly these simulations can be configured to take into account internal system variability, external forcings, but also code in anthropogenic influence. So as you all probably know, there are a number of RCP scenarios that one can explicitly code into these simulations and run them out till the end of the century. And then you'll be looking at the question of how do I analyze these large data sets and automatically extract extreme weather events. So climate simulations are fundamentally the tool, the source of our data sets, because we're going to be asking questions about what's going to change in the future. So now the question is, if I give you a 10 terabyte climate data set, which is say a 25 kilometer resolution, it's multivariate, so each grid point has dozens of variables. How are you going to objectively pull out extreme weather events in such a data set? So really, this is a pattern detection task. It's a classic pattern detection task. And the question that this talk will explore is, can deep learning come to the rescue? Can deep learning help out? So I want to give you a visual sense for what the data set looks like, just so you know, I guess how hard or easy the problem might be. So think of a CAM5 quarter degree simulation. This is just a single field, the integrated water vapor field. And this simulation is just a few months, but essentially we run this out for about 100 years or so. And your job, I guess the computer vision systems job, the pattern recognition task is going to be, given this data set, find for me, I'm just going to play this simulation once more. So given that simulation, track the hurricanes, track the extratropical cyclones, track atmospheric rivers. So that's going to be your task. So the times we store data at every 3-hourly resolution. That's typically what we have available to us. So this is a climate simulation. That's what we That's at least what the community seems to refer to it as. Mm-hmm. Yep. No, that's right. That's right. So again, it depends on, I guess, how you do the analysis. This is a first principles PDE solver. That's the time step. I think is much finer. Michael can correct me if the native time step for CAM5 is a few minutes, 450 seconds. But we cannot store data at that resolution. So we store data every 3 hours. And then, of course, the integration period is much longer. So again, running it for many decades or a century is not unheard of. Now, given such a high fidelity, high temporal fidelity simulation and also spatial fidelity, how you choose to analyze it is up to you. All right, so hopefully you have a sense for what the visual complexity is of this data set. So let me now just quickly turn to deep learning for computer vision. Again, if you've been following the news in AI or deep learning at this point in time, you may know that this is an extremely hot field. So I want to just talk about what's going on there. So for the canonical computer vision community, the tasks that they are interested in are to look at images, and within images, solve a few problems. So classification is a problem, wherein if you give an image, the task of the computer vision system is to say, is there a cat in this image or not? Localization is about, I not only do I want to know what's in this image, but I want to actually have a tight bounding box around the object of interest. The reason why this is important for climate is because if you take any snapshot, chances are there are going to be multiple extreme weather events. So you do want a tight bounding box and localize the event of interest. Object detection is the problem wherein, again, given an image, there might be multiple kinds of objects in the image. So you want to have multiple tight bounding boxes around multiple events. And finally, segmentation is a problem wherein you actually pull out the pixel values corresponding to every single object. So that's the task. So we're gonna in this talk we're gonna be focusing on the object detection problem. So I have this nice CAM5 image. I know that there are multiple kinds of extreme weather events, and I'm going to be looking for tight bounding boxes around the extreme weather events. So this problem, of course, has been looked at for a while in computer vision. So in this image, in this slide, for example, there are 4 natural images of the world. And the computer vision system essentially is trying to do the following. Given this image, is going to try to draw a tight bounding box around a bird or a frog, a person, a chair, a dog, so on and so forth. Now, this is a hard problem. So in order to solve this problem, the computer vision community essentially came together and created this data set called the ImageNet data set. It was created by Fei Li in Stanford, wherein they essentially labeled 1.2 million training images. And there is really an impressive amount of visual complexity in the data set. So it may be a little hard to pick this out, but there are images of the outdoors, yachts, trees, so on and so forth. So really, 1,000 object classes under realistic acquisition conditions. So in about 2011 or so, Jeff Hinton and some of his students in Toronto created something called the AlexNet architecture. It's named after Alex Krzyzewski. And they essentially created a deep neural network. So you essentially have an input image here. So it might be, say, 224 by 224 pixels and 3 channels. And you pass it through a number of filtering operations. So there is a bunch of convolution, there are a bunch of pooling operations, and you keep doing that till you reach the end. And at the end, you ask the network to predict what object is in the image. That's essentially the task. Now, there's an important departure here, I think, in deep learning in general, but also in this architecture, wherein people actually gave up on hand-tuned features. So for a long time, for maybe 2 decades, essentially what the computer vision community used to do and what the climate science community is doing right now is they thought that they could by hand design what the best face detector might be, or what the best pedestrian detector might be, or what the best bus or car detector might be. So in this case, they essentially gave up on that problem. And what they did was, well, instead of hand-tuning features, all we're going to do is to provide 1.2 million training examples. We're going to just create this architecture, randomly initialize the weights, pass the input data, filter it through, compute the output, compute the error, and then back propagate the error through the network, updating the weights. And the hope is that the network would converge to something reasonable. Now, interestingly enough, it did. And I think that's the reason why a number of neuroscientists and certainly computer scientists got all excited about it. So when you look at the weights that have been learned after massively training this architecture, the weights actually make sense from a visual systems perspective. The convolutional weights in the very first layer correspond to the Gabor filters. If you go one layer up, the convolution layers, the filters essentially look like very simple texture patterns, so compositions of edges. You go higher up and look at some of the layers which are further along. You essentially start getting object parts. So things like clocks and faces and parts of cars. And then the final layer, of course, corresponds to object parts, corresponds to entire objects. So this is interesting because a priori, they did not really build in the notion of composition. They did not build in the notion of what might make for an interesting feature. But all of that essentially emerged from the training process. So this is really interesting. But the better part really is that the performance of these methods is just tremendous. So for a long time before 2011, every year for this competition and also other related competitions, the entire computer vision community would come in and they would try to improve the classification error by 0.1% or 0.2% or 1%. So that was a big deal. But suddenly in this year when AlexNet was proposed, the error rate dropped significantly. And subsequently, every year, people have essentially been changing the architecture a little bit, and the error rate has been substantially decreased, to the extent now that it's believed that the human level performance for this task of image classification might be at the 5% error rate. And now these systems have certainly exceeded that. So now the error rate is around 3% or so. People really didn't. So a lot of computer vision experts did not believe that this was possible, that this could be done in this decade or maybe even in the next decade. But this was really a watershed moment. And really, I think this is what has led to the AI and the deep learning revolution. So, Sunny, so hopefully, you have a sense for what's going on with deep learning and computer vision. So the question that we asked ourselves about 3 or 4 years back was, we saw this coming. I mean, we saw this phase change in the quality of results. And the question we asked ourselves was, well, can deep learning work for climate science, in particular for pattern recognition tasks? So certainly there are some similarities. If you just think about the climate data set as a multi-channel image, there are some similarities in the tasks that we want to solve. So we care about pattern classification, localization, detection, segmentation. Also, in some cases, we care about clustering. Feature learning is a fundamental prerequisite for all of these tasks. But there are some differences. So our data sets are not 8-bit 3-channel images. So our data sets have many more channels. They are double precision floating point typically. The kinds of features that we have different spatial and temporal scales. So if you look at a hurricane, maybe a 200 by 200 kilometer box is sufficient, but extratropical cyclones are thousands of kilometers in size. The fingerprint of El Nino might encapsulate an entire ocean. So there are some differences. So there's a question of can deep learning really work in this context? But the last point that the underlying statistics of patterns in natural images. So if you go around with a image with a camera taking images of the natural world, and if you look at the underlying statistics of a fluid flow simulation, the underlying statistics are very, very likely different. So how points cluster up in a high-dimensional space, the geometry of the classifiers is going to be different. So really, I think as a statistical device, the question is, can deep learning capture that complexity? So this is just an indication of the multivariate nature of the data. So again, if I just look at a patch in our prototypical CAM5 image, then there are many different variables that one has to look at. All right, so now I'm going to come back to climate science. So our experiments with deep learning for detecting extreme weather events in climate science data. So essentially the task is going to be formulated as the following. I'm going to give you a CAM5, the computer vision system, a CAM5 image. And the eventual task is going to be draw me bounding boxes around different events. So here's a green bounding box around an extratropical cyclone. These are 3 bounding boxes of different sizes around tropical cyclones. And then this is a bounding box around an atmospheric river. So that's going to be the grand challenge problem that we'll try to solve. All right, so but we need to start slow. So first of all, the question of whether deep learning can work at all for fluid flow data is not clear. So we'll start simple. So we'll start with a supervised binary classification problem. So essentially what I mean is the following. We're going to create an architecture and we're going to give it training data. And the training data is going to be conveniently cropped, centered, multivariate patches. And all of those patches are going to have labels. So for simplicity, let's just focus on tropical cyclones for the time being. So I'm going to give the deep learning system, say, 5,000 examples of cropped centered image patches that I know have tropical cyclones. And then apart from these positive examples, I'm going to have a bunch of data that's negative examples. So I know for a fact that these don't have tropical cyclones. So given all of that, 10,000 positive examples and 10,000 negative examples for tropical cyclones, can I train a network? And if so, the task I'm going to give the network is I'm going to give you a held out test patch that the network has never seen before. And I'm going to ask the network to predict, is there a tropical cyclone in this patch or not? Yes or no. So that's the binary classification task that the network needs to solve. So some sense for the training data. So again, for the tropical cyclone task, the image patches are 32 by 32, a bunch of variables coming from CAM5. And then about 10,000 positive and 10,000 negative examples. And we'll have similar tasks. So a separate network is going to be trained for tropical cyclones. A separate network is going to be trained for atmospheric rivers and weather fronts. So for the, say, the tropical cyclone case, this is what our network looks like. So again, there is an input data set, an input layer. And that's 32 by 32 by 16 or so channels that we have. Then there is a sequence of a cascade of convolution layers followed by pooling, convolution followed by pooling, a fully connected layer at the end, and then this binary classification score that the network needs to predict. In general, I think what we found as we've gone about this investigation is that we really don't need very, very deep architectures for climate data. So unlike AlexNet or ResNet or some of the state-of-the-art computer vision networks, which have sometimes now even hundreds of layers, we seem to be able to get away with just 5 or 6 layers. That seems to suffice. So some results. So for this, again, supervised binary classification problem, the deep learning results, the convolutional net results are here. So you have the training accuracy and then the test accuracy. But just for comparison, again, we did do the due diligence and use some canonical machine learning methods, so logistic regression, k-nearest neighbors, support vector machines, and random forests. So a few high-level observations, I guess. So far, across the board, I would say that the numbers are fairly high. I mean, the accuracies are all 85% plus. So I think what that tells me is that in general, this is an easy task. This is really not a very hard task. And I think what this also implies is that maybe the climate science community has not paid a lot of attention to machine learning because this problem could have been solved, I think, a long time ago. So apart from that, I guess the numbers, I would say, across the board seem to be around the best, I would say, with deep learning compared to other methods. I mean, once in a while, I guess a random forest will do fairly well. But across the board, deep learning seems to do fairly well for tropical cyclones, for atmospheric rivers, and for weather fronts. So again, near perfect accuracy for tropical cyclones and 90% and 90% also for ARs and weather fronts. I believe that the accuracy can be increased even more. But anyway, I mean, that's an investigation that we are conducting. I'll note that this is a very important point. Along with all of these methods, there are always a few knobs that one can turn. So for k-nearest neighbors, you need to somehow figure out what the right choice of k should be. For support vector machines, you need to figure out the right form of the basis, the kernel function. For random forests, you need to figure out what the right depth should be and how many variables to use. For convolutional networks, there are many different knobs that one can turn. So it is really important that one have a principled way for setting these knobs. And in this case, this so-called hyperparameter optimization problem was solved with the software called Spearmint that we've been using. All right, so I think that exercise essentially convinced us that deep learning could operate successfully on fluid flow data, on atmospheric simulation data. So then we decided to take things up a notch. So really, we realized that what we want to do here is not to create 3 separate networks or 10 separate networks for detecting 10 different events. What we really want is to have a single unified network that can work for all weather patterns. Now, apart from this pattern classification problem where you have these conveniently cropped centered patches, which is not going to be the case for us, you really do want the network to predict the right bounding box, so the center of the bounding box and the spatial extents for these weather patterns. And finally, this is a grand challenge problem. I wouldn't say that we've solved this in any way, but the observation still remains that well-studied phenomena like tropical cyclones, you might have a lot of labeled data for those, but there are going to be weather event patterns for which you're not going to have a lot of labeled data. So really what you would like to do is to create an architecture that can potentially discover new patterns or operate in the regime of having very limited data for a few patterns. All right, so this is the semi-supervised architecture that we came up with to target this particular problem. And I'll note that this is joint work with the University of Montreal. And the observation here is the following. You have essentially an autoencoder. So you have input data, and then you filter it, so using the convolution and pooling layer logic that we've been talking about all along. So there is an encoder piece. Once you reach a compact description of the features, then essentially you ask that compact description to predict the label for a weather pattern and the bounding box size. So this is from left to the center to the bottom is your classic supervised architecture. The data for these bounding box labels and sizes come from a toolkit called Tika that we've been developing for a while, which essentially encodes human criteria, expert criteria for what makes for a tropical cyclone and atmospheric river and so on and so forth. So from left to the center to the bottom is a supervised formulation. But really the interesting piece is from the left to the right, which is this decoder architecture, wherein you take this compact description and then you decode it to create an image that's of the same size as the input image. So say if your CAM5 images are 1152 by 768 by 16, so we're going to create an image that's 1152 by 768 by 16. So this architecture is going to simultaneously try to solve for 2 objectives. One objective is the reconstruction loss. So having forced this architecture to do the downsampling and then the upsampling, in simple words, it'll try to create, the objective is going to try to minimize is the difference between the L2 norm between the output image and the input image. So that's one reconstruction objective. The second objective is going to try to solve for is to essentially try to make its predictions as accurate as possible. So get the class labels right and get the bounding boxes right. If the network succeeds in doing this task, so simultaneously solving these 2 objectives, then essentially what that means is that this bottleneck layer has been in fact successful in capturing all of the interesting variability or all of the interesting patterns, because after all we are going to be asking it to predict where the patterns are and the bounding boxes, and essentially the decoder is going to be operating on this layer directly. All right, so we created this architecture, we trained it. So I want to show you some results. And again, this is work in progress. By no means are we completely done, but it's looking promising. So some sample results, I guess. So on the left, 4x4 panel essentially indicates CAM5 raw output. So this is what we feed into the network. And then the output, the reconstruction, having gone through the autoencoder, is on the right. So in general, the spatial variability of the patterns is being captured fairly well by the semi-supervised architecture. Now, how about the classification and regression results? So in green is the ground truth for what Tika says where the patterns are. So green boxes. So this is a green TC, a bunch of tropical cyclones here. a green atmospheric river, a green extratropical cyclone, a green extratropical cyclone here. And then red is where the network is, this semi-supervised architecture is predicting where it thinks the patterns are. So a bunch of tropical cyclones, atmospheric rivers, and extratropical cyclones. So in general, I would say that's, in terms of the spatial location, we seem to be getting that right. The label seems to be okay. But the size of the event is not quite there yet. And we know that there are some limitations in the training process that is preventing this architecture from exploring the scale of bounding boxes effectively. So that's something that we are looking at right now. Now, this holy grail problem of, can we potentially discover new patterns from the semi-supervised architecture? So again, this is not solved by any means, but I just wanted to highlight, I think, what a potential result might look like. So remember the bottleneck layer, that's the most compact description of all of the features. So this is a T-SNE visualization of the clustering structure of that bottleneck layer. And essentially what I was hoping is that the colors here would, essentially blues indicate tropical cyclones, I believe, and greens might be extratropical cyclones, and red are atmospheric rivers. What I was hoping was that we would get a clear separation of tropical cyclones. All the blue dots would be in one cluster, and then ETCs would be in another cluster, and ARs would be in another cluster. But that's not the case right now. So anyway, so there's work to do in terms of separating stuff out. But I guess let me just highlight where we are going with this. Should we succeed in separating these clusters out, the question then becomes of coherent structures, coherent clusters that don't yet have a label assigned to them. So essentially the scientists, the climate data analysts would come in post hoc, examine these clusters that don't yet have labels assigned to them, look at the spatial boxes corresponding to these events, and then see if they can provide a tag or a label to them. All right, so I'm going to move on to a slightly different case study. This comes from Ken Kunkel and Jim Beard, who've been working with us on, again, the use of convolutional architectures, but for a slightly different problem. So in this case, what we're doing is to take a spatial grid over North America, and then on a grid cell by grid cell basis, we're going to try to predict weather fronts. So we're going to try to predict if there is a warm front or a cold front or an occluded front, and the level of confidence, I guess, that we have associated with the prediction. So again, the same logic. We've trained a convolutional architecture. Ken's group has done a great job with creating ground truth data sets for these weather fronts. So we trained a convolutional architecture for those for fronts. So on the left is essentially ground truth as labeled by humans. And then on the right is what the convolutional architecture is predicting, where it thinks the fronts are and their type. So in general, again, the results are pretty good. In fact, it turns out that humans don't tend to be very careful over the oceans for weather fronts. And there seem to be more discontinuities in human labeling, but the convolutional architecture doesn't suffer from such biases. So anyway, so this is looking promising, and we're going to be looking at some more at this. So I want to just give you a summary of where this work is right now. So there are 2 papers that we have currently under review. Ken, myself, Michael Wehner, and others have written what I believe is the seminal article on deep learning for detecting extreme weather patterns. So it's under review. We also have a submission at NIPS, which is under review on essentially a data set for enabling researchers to access the data reference architecture and then do their own innovation. We are trying to apply this, as I mentioned, to the front detection problem and also for atmospheric rivers, so that's coming along. But there is another exciting development, which is scaling deep learning. So it turns out that it takes a long time for these networks to converge to something reasonable. So for tens of gigabytes of data, it can take us many days, sometimes maybe even a week. So we have now figured out how to get deep learning to scale. So there is a paper now at the supercomputing conference on scaling the semi-supervised architecture that I just presented to an entire supercomputer. So as was mentioned in the introduction, I work at NERSC, and NERSC has this Cori Knight's Landing supercomputer that has 9,600 nodes with about 600,000 cores. So we now have deep learning scaling and running on the entire machine, and we've been able to achieve 15 petaflop performance while doing this training. All right, so some next steps before I move on to speculation, I guess. So our goal is to create a unified architecture that can find all kinds of extreme weather phenomena in all climate data sets. And by that I mean observational data sets, satellite products, reanalysis products, simulation output. We are envisioning that maybe if the community can help out with contributing to a labeled data set, then we can train this unified architecture and get the best performance that we can on all climate data sets. So in order to achieve this goal, clearly we need a schema for capturing labels and essentially make this data set widely available. So that's something which we are working on right now. And then also the architecture that we've created for the semi-supervised problem and also the supervised problem, we're trying to release that to make that accessible to researchers like yourself. Now, so far we've purely looked at convolutional architectures, and we've purely looked at the detection problem. We treat every single image instance independently of others, but there is clearly a temporal structure to storms. So capturing that is important. So one of the things that we're looking at is a hybrid LSTM and convolutional architecture for storm tracking. And then also, I think I've convinced myself that classification is working. We seem to be getting reasonable results with localization. Detection, there's some more ways to go. But segmentation is obviously the next step. So that's something that we're looking at as well. Some open challenges. Again, this area is moving really fast. Essentially, researchers communicate, their papers to each other with Twitter feeds and whatnot. So anyway, so before you just dive right in, I think it's important to note what challenges one might encounter. So hyperparameter optimization is a big challenge, and really there are very few people who have an intuition for how to tune the network. How do you decide how many layers you're going to put in, how many filters you'll have, how the learning rate is going to vary, so on and so forth. So that is definitely a black art at this point in time. I mentioned performance and scaling. To some extent, we at NERSC have that under control. Scarcity of label data is a big challenge. So again, deep learning operates in this paradigm where you have a lot of training data. So really, I think it's just a matter of time before the community realizes that this will work. But really, the community has to self-organize, and then run labeling campaigns so that we can produce a lot of training data. But I think even then, we are likely not going to be in this regime of 1 million labeled images. I don't think that's going to happen for climate science. So really, we are likely going to be in this paradigm of semi-supervised learning, wherein we have a bunch of training data, but most of the data is actually unlabeled. So really understanding around what the theoretical limits are of semi-supervised learning, I think is going to be important. Finally, this last point is I think really important for climate science, which is this issue of interpretability. So if you look at techniques like logistic regression or support vector machines or k-nearest neighbors, I think the neat thing about those methods is you can interpret. You can pretty much explain to other people, your colleagues, on what these methods are doing. It's not as simple with deep learning. A lot of tools are being developed for visualizing what features are being learned and how the features are composed. But I think one can state that at this point in time, these are really black box classifiers. So really the proposition I think that we are putting forward to the climate community is, you can throw away your decades worth of heuristics, which are imperfect, but I'm going to give you a perfect classifier, but it's going to be a black box. Is that going to be an acceptable proposition for climate scientists? So going forward, I think we really have to somehow incorporate domain science principles. There are many laws of physics that we've known for millennia. There are PD solvers subscribe to physical constraints, but these networks have no notion of physical consistency. You randomly initialize the weights and you stochastically update them. So the features you end up with, there is no guarantee that they subscribe to laws of conservation of energy or momentum or what have you. So somehow I think we'll need to bake in physical consistency into these networks so that the output is a little more interpretable. All right, so I'm going to speculate, and I think I was encouraged to do that by the organizers, on what the future of AI and deep learning might look like in climate science. So if I look at the timeline of these two communities, computer vision and climate science, and specifically I'm just going to be focusing on pattern detection. Um, Really, the field of computer vision has gone through a lot in the last several decades, right? So late 60s is when the first neural nets were proposed. Neural nets in that decade could not even solve the exclusive OR binary logic problem, so they died an untimely death, only to be born again in the mid 80s when you had multi-layer perceptrons and then back propagation rules were figured out. That's what enabled neural nets to become deeper. Uh, People I think in that decade had, and I would say even in the early 70s, had idealistic notions of using first principles and physics to really reconstruct 3D geometry. That never really quite happened. So the field then moved on to more advanced, analytics techniques, machine learning techniques. So techniques like random forests and these hand-tuned features like SIFT and HOG and fancy edge and corner detectors were created. The field then moved on to support vector machines. The community started to come together and create these labeled data sets. So there was the Pascal VOC challenge. Finally, in this decade, the ImageNet data set came about, and these big competitions were organized. And then, of course, the AI deep learning revolution just took off with AlexNet and ResNet and so on and so forth. So really, I think as you look at these past few decades, there's been a lot of innovation on methods, and I think the community realizing that individual researchers sitting in their individual labs can produce as many papers as they want, but really until and unless there are some standard benchmarks and large data sets that are made available to the community, it's only then we can objectively assess whether the community is actually making progress. Now, compare that to pattern detection in climate science. Really not much has changed. I mean, we still have hand-tuned features, right? So we'll have a few tropical cyclone experts who are going to say, use vorticity threshold of 1.6 times 10 to the minus 4 and detect a temperature warm core and have this pressure gradient, and we'll declare it as a tropical cyclone. Atmospheric rivers, I mean, there are similar criteria that are used. Extropical cyclone, there are a few dozen algorithms with no consensus on what makes for an ETC. So people often resort to quote unquote first principles physics, but really the choice of thresholds is never really well justified. Now, once in a while, the community will try to come together. So there's the IMILAST exercise that happened for comparing different methods for detecting extropical cyclones. Michael Weiner and others are conducting an exercise on atmospheric rivers and establishing some consensus for how well these methods are doing. But in terms of the innovation, in terms of new methods from machine learning, there's really not much that's out there. So really, I think my hope is in our work and in others, I think it's time to bridge some of the gaps between these two communities. I think the computer vision community has just exploded and taken off. So it's high time that we let the data speak for itself. And if our climate science community can come together and present some, gel around some data sets, we can see how well these deep learning methods work for climate science. All right, so looking forward though, and I'll just insert a disclaimer that's always risky to make predictions about the future. I think that in the next few years, I think the climate science community will actually self-organize and to some extent, I think, run labeling campaigns. Groups like Ken Kunkel's group have spent decades in creating data sets for weather fronts. There are other groups that have data sets for tropical cyclones, and other groups care about extropical cyclones and so on and so forth. So really, I think we just need to have one common data set where all of this can be put together. I think that for the next few years, researchers will exploit a lot of low-hanging fruit. I mean, we've done that, getting 99% accuracy. I mean, how often do you do that out of the box? So I think what's going to happen is that we'll collectively realize that classification problems, clustering problems, and some regression problems are going to be completely solved. That's probably what's going to happen. And I do think that these tools are going to be broadly applicable to analyzing both observational and model output. So thinking a little bit further out, I do think that such tools are going to be deployed broadly at HPC centers like NERSC in the cloud. Google already has TensorFlow available, and universities. Certainly, I think when I think about my job at NERSC, our goal is to make sure that scientists can do interactive analytics on 100 terabyte data sets or even petabyte sized data sets. So imagine that you can press a button and get this network trained and the network run or tested on a large data set. What could you do then? So we do believe that entire climate archives, so again, if we assume for a moment that classification, segmentation problems can be solved completely, I do believe that entire climate archives can be segmented and classified. I mean, that can just be done. And now the question maybe for you is, as an advanced statistician or as an advanced climate data analyst, what can you do with it? So I do believe that the nomenclature for the kinds of analysis that you do is going to change. When you do correlation analysis, it's not going to be about how does one pixel correlate with some other pixel around the globe. You're going to be talking about correlations of the ENSO with tropical cyclones, or some blocking event with a hot wave. So the semantics, I think, of the analysis is going to change. Anomaly detection is going to become, I think, more interesting. And certainly, I think hopes of doing causal analysis, that's going to become, I think, more interesting down the line. So I mentioned that there's a lot of low-hanging fruit, but I think there are some hard questions as well. So really understanding the limits of unsupervised and semi-supervised learning, incorporating domain science principles into these architectures, thinking hard about interpretability and getting that to work. Those are likely going to be addressed, I think, in 3 years out. So I'm going to, I think, maybe just encourage you to think around what is the value add of you, the data analyst, in this paradigm. If problems like segmentation and clustering and regression are all solved, what do you bring to the table? So so this is what we think that a workflow might look like in the future. You have a big supercomputer, like say the one at NERSC. You have an embedded artificial intelligence deep learning system that's easily able to run on these machines, and it can do that even so right now. NERSC already has a lot of data sets, so we have pretty much, well, a lot of CIMI5, a lot of observational data. And now you can assume that all of this is segmented and classified. That's all done. So what is the scientist doing here, right? So I think what the AI system can provide to the scientists are patterns and clusters and anomalies. Anomalies might be things that the network is struggling with. And the climate scientist provides for labels. I mean, they provide semantics. This is what we're going to call an atmospheric river, and this is what we're going to call a front, and so on and so forth. So I think I do see some value there in human language, in providing semantics and some conventions. I think there will still be a need for interactive exploration. So I think if one can do interactive analytics on all of CIMI5 and so on, I think one will start asking, I think, many more questions, which are just not possible to do so right now. But I do think that fundamentally it's going to free up the climate scientists from the drudgery of moving data around and downloading it and pre-processing it and coding up hand-tuned features and so on and so forth, to really think hard about mechanisms and propose hypotheses, which I think is really not, unfortunately, not happening right now. I think right now when I look at some of my colleagues in UC Berkeley and even otherwise in the DOE, they'll have a certain hypothesis, they'll propose that, they'll ask Michael or someone else to create an ensemble, run that out, do the analysis, and this whole cycle takes many years. So I think there is a hope that we can cut that down dramatically. All right, so just to conclude, we looked at the problem of characterizing extreme weather. I believe that characterizing extreme weather in future climate regimes is important. Hopefully you're convinced that deep learning can be applied effectively to solve this pattern recognition problem. So we have supervised and semi-supervised convolutional architectures working. We're looking at extensions of these architectures to get at segmentation, but also look at LSTM variants to take time into account. There are some unique challenges that come up when you look at the intersection of deep learning with climate science. And those challenges are around performance and scaling, interpretability, hyperparameter optimization, and lack of label data. So really, I think there's a lot of room for innovation. I think there's a lot of room for high impact science here. And we are open to collaboration. So if you have any ideas on on any of this, do let me know. So I'm going to be around today and tomorrow, so please feel free to catch me. A number of people to acknowledge. Clearly, this is not my work alone. So a number of collaborators from Intel Research, Stanford, UC Berkeley, Mila, Berkeley Lab, and NOAA. And again, Michael and Ken are in the audience today. All right, I'm open to questions at this point.
I'd like to keep this on schedule, so I'm going to propose something a little bit different. I